Assalamu alaikum. So we start with our next lecture on theory of errors and weights. So basically in this lecture or in this topic we'll be concentrating on the types of errors that we encounter in our servering projects and how to deal with them. Because errors are imminent, they will be there, and usually we've been dealing with them before as well, using some checks that we apply to close traverse mostly and to open traverses as well. But in simple measurements, there are no checks that we can apply directly. So that is when we can use this method of using probability of those errors actually occurring and how do you deal with them. So these methods are not limited to serving applications. So this is basic statistics and it has numerous applications. So the theory of probability has numerous applications. So it's not just limited to your serving observations. So before we jump onto that, first we'll discuss what different types of errors are possible, and also what do we mean by theory of weights. So it says that errors are imminent. There will always be errors whenever you take measurements, and the aim is to keep the errors in a tolerable limit. So they should not exceed some limit which you set by yourself, but that tolerance limit depends on the different types of project that you do. So the key is that they shouldn't exceed that. So what are direct and indirect observations? Direct observations are what you take yourselves directly. So for example, applying a measuring tape or using a measuring tape or taking a reading without any equation or anything, just direct measurement. And indirect observation would be where you don't take the measurement by yourselves, but you deduce the measurement using some relation. So let's say I want to find out the height of a tree, and I use a theodolite, and I then use determine the distance between theodolite and the tree, and take the angle of elevation, and then determine the height of the tree indirectly. So that would be an indirect observation. So the thing about indirect observations is that if there is error in the direct observation and then you use that measurement again and again, so that error keeps on multiplying to all the indirect observations that you make by using that direct observation. That error keeps on multiplying. So that actually signifies the importance of finding out errors and dealing with them. So what is an error? So error is the difference between a true value and the observed value. So let's say there's a distance between 2 points and it's supposed to be 30 meters and you measure it as 29 meters. So your error would be 1 meter. But that's the most general equation of an error, true value and the difference from the observed value. But the thing is that no observation is exact. That means every observation contains errors and the true value of an observation is never known. And the exact error present is always unknown. So I said that the distance between 2 points is 30 meters, right? But how did I get to that value? I mean, I use a measuring tape to measure that, but what makes it a true value? What makes it say, yeah, this time when I took the value, it's 30 meters, that's correct. And the next time I took it as 29 meters, why isn't that the true value? Why is 30 meters the true value? So if you're using the same instrument and the same person takes a number of readings, so let's say he takes 5 readings, so which one is actually the true value? That's always unknown. That what bases the whole concept on. So we need to differentiate mistakes from errors. So mistakes are blunders, you can say, caused by misunderstanding the problem or carelessness or so on. But it's different from errors. See, because mistakes can be rectified, but there will always be errors in your observations. And what are the sources of the error and what are the types? So the number one source is natural errors which are caused by atmospheric conditions such as wind, temperature, humidity. So we studied this before as well in the case of EDMs, in the case of uh, auto levels and theodolites as well. So you have a refraction value for the air, and it can cause your readings to be erroneous to some extent. Similarly, if there's wind, it can cause the leveling staff to sway. So these are natural errors, right? And you also study more about it in GPS as well. And then we have instrumental errors. It results from any imperfection in the construction or adjustment of instruments and from the movement of individual parts. So if you can find out the error in the instrument, then you can apply a correction because that instrumental error usually remains the same in every measurement, depending on the type of the error, but usually it remains the same in every measurement. So what you can do is you can determine that error and you can apply that set correction to every measurement. So you can take care of instrumental error. And then we have personal errors, which are solely due to the person taking the reading and how expert he is or what method he's using and all of that. So then we have systematic errors. So systematic error is a broader term and it can be applied to a number of reasons which cause the error, which includes environment, the instrument, and the observer. So these are the errors which actually you can do something about. So if it's because of the environment, you can apply the correction for refraction or correction for wind or correction for temperature. So we've studied about these corrections. If it's due to the observer, then obviously you can get a more experienced person. If it's because of the instrument, you can find out that error and you can apply a correction to every reading because instrumental errors remain the same. So all of these in the broader realm are called as systematic errors, and these are something that you can actually do something about, and you can reduce them or nullify their effect. So these are systematic errors. But then we have random errors. So these are the errors that we are going to talk about for the rest of this topic, because there is no cure for these errors except for applying the theory of probability. That what is the probability of this sort of error occurring? It will always be there, but depending on the magnitude, what is the probability of occurrence? So random errors are those that remain in measured values after mistakes and systematic errors have been eliminated. So once those errors are eliminated, the remaining error is called as random error. So they are caused by factors beyond the control of observer. They obey the laws of probability and are sometimes called accidental errors. They are present in all surveying observations. So the magnitudes and algebraic signs of random errors are matters of chance, and there is no absolute way to compute or eliminate them, but they can be estimated. Random errors are also known as compensating errors since they tend to partially cancel themselves in a series of observations. So, for example, um, if you are reading off a leveling staff and the crosshair is between 2 points, somewhere between 4 and 5, right? Just an example. And sometimes if you take the reading as 5 and sometimes you take the reading as 4, depending on your own assumption that the crosshair is closer to which value. So some if you take a number of readings again and again, sometimes you'll be reading it as 5, sometimes you'll be reading it as 4. And this is no fault of the observer. This is just by chance, by random occurrence. So what they say is that if you take a large number of readings, the effect would be cancelled out. So that is how random errors work. Now, precision and accuracy, we'll be talking about these two terms a lot. Um, so before that, dispersion is the difference between two observed values of the same quantity. A small discrepancy indicates that there are probably no mistakes and random errors are small. However, small discrepancies do not preclude the presence of systematic errors. So if you take the same reading again and again, if there are dispersion between the results, that means there could be random errors, sorry, systematic errors, and there are definitely random errors. So if you then negate or nullify the systematic errors or take out their occurrence, then you'll be left with random errors only. And they say that if the dispersion is small, there's a good chance that there are no systematic errors and there is just random error. But you cannot obviously rule it out completely. And precision refers to the degree of refinement or consistency of a group of observations and is evaluated on the basis of discrepancy size. So let's try to understand it from this figure over here. So let's see the figure number A. And over here you see targets and shots. And if you see over here, the shots are all very close to each other. That means there is very little discrepancy, and these shots are very precise. In the figure B, the all the shots are very far away from each other, so discrepancy is high. That means they are not precise. And in C, again, they are very close to each other. That means they are precise again. So this is how precision works. If you take five readings and they all of them are very close to each other, that means the work is very precise. And if the five readings are very far apart, that means the work is not precise. But it doesn't tell you if the work is accurate or not. So that is where the bullseye comes in, the center point. So in A, although the shots are very close to each other, but they are very far from the bullseye. That means they are precise, but they're not accurate. In part B, they are not precise and they are not accurate as well. And in C, they are both precise and accurate. So accuracy means how close your observations are to the accurate, correct value. And precise means in a set of observations, how close the observations are to each other. So now comes in the probability. So you have studied probability before, I hope numerous times. And probability, what it is, it's the occurrence of one particular event divided by the occurrence of all possible events. So that is probability. So it is a ratio of number of times a result should occur, your favorable result, and divided by the total number of possibilities. So it says that because of equipment on observer imperfections, exact observations cannot be made. So they will always contain random errors. So that's what we've discussed. And the magnitudes of these errors and the frequency with which of a error of a given size occurs follows the law of probability. So this is where we are going to bring in our understanding of probability. So let's say there is one angle that needs to be measured, and I ask anyone to measure that angle 10 times. And he gives me 10 values of the same angle. Then I perform analysis on those 10 readings, and then I can come up with the expected error. That means the next time I send the same person in to take that same reading, I can say with some data or with some figures that this is the probability that the next reading that this person will give me will be in this range, or it will be this much far apart from the true value. So that is how you can use the data that you have to run analysis on that data, and then you can give out predictions about the future data or predictions about the future observations by using probability, which has been evaluated using the data that you have. So most probable value or the true value. So this is where all that talk about that the true value is never known and you don't know which value is the right one. all that talk comes in. So if you never know the true value, how can you estimate the error? Because the equation of error is that it's the difference between the true value and the observed value. So let's say if we talk about the same angle, if that angle's value should be 80 degrees, and then I ask five people to give me five readings, so I can subtract each value from the true value, the true angle, which is 80 degrees, and I can calculate errors for everyone. But the problem is, how do I know that the true value is 80 degrees? So that is where the most probable value concept comes in. So since true value can never be known or calculated, most probable value can be calculated if redundant observations have been made. So before sending you guys in to take that value, let's say before that, I took 30 values myself, 30 observations myself, and then I took the average and called that as the most probable value. So see how it's not, I'm not calling it as a true value, I'm calling it as the most probable value. So by taking redundant extra observations, the more observations you take, the better. um, it will bring the most probable value closer and closer to the true value. So that is how it works in your favor. So yeah, so this is how you come up with the most probable value, which can actually work as a replacement for the true value, and then you can calculate the errors, and then you can apply your analysis. So since now we're working with the most probable value and not the true value, so we would say that a residual is the difference between the most probable value and the observed value. So now we're not calling it as error, we're calling it as residual. And because we have replaced the true value concept with the most probable value concept. So the residuals, rather than errors, are the values actually used in analysis and adjustment of survey data. And if you remember in the beginning, we talked about how if you are taking a reading between 4 and 5, and you would be sometimes inclined towards 5 and sometimes towards 4. And let's say the true value, or not the true, the most probable value is 4.5. So sometimes you had taken readings above 4.5 and sometimes below 4.5. Uh, the theory states that in a very large number of observations, the sum of residuals would be equal to zero, because sometimes the residual would be positive, sometimes would be negative, and if you sum it up, the difference would be equal to zero. So once we have these residuals, what can we do with that data? So let's say you have an angle observation and you have 10 observations, or more than that. You have, if you see this table over here, in the first column you have observed value, in the second column you have, I think it's a number of observations, and the third column you have the residual value, and then the same thing repeats. So if you take a number of observations and then you calculate residuals, so you have now data in which you have multiple values. And I want to plot this. I want to plot that what is the frequency of occurrence of these residuals. And let's visualize this with the help of this graph, this histogram. So basically what it's giving me is that on the y-axis, it is giving me frequency of occurrence. And on the x-axis, it's giving me the residual value. So what we have done is that we have taken these observed values, calculated their average, called that average as the most probable value, and then from the most probable value, we have subtracted all of these observations one by one, and then calculated the residuals that you see in these columns. Then what we have done is that we have plotted a graph between frequency of occurrence of a residual on the y-axis, and on the x-axis we have size of the residual. So instead of um, plotting the actual residual value, we create bins or we create intervals. So over here on this graph, if you see that over here we have an interval between positive 1.75 residual to positive 2.45 residual, and the interval would remain the same in every case. So this is a range of values 1.75 to 2.45. And then I see from the table on the previous slide that how many residuals fall in this range. So let's say that the number of residuals in this range are 8, right? So over here, I will get this point. Similarly, for some other residual, let's say plus 5.25 to positive 5.95, the number of values are 1. So that means the frequency is 1. So I'll plot this value over here. So if you see how this graph works, that when the residual is 0 or close to 0, the frequency is maximum. So that means most of the times your reading would be close to the average. That's why it's the average. That's why it's the most probable value, because most of the values taken previously as well are close to that one value. So for the next values as well, um, most of the values will be close to that. So the residual will be close to the zero value. So that is why the frequency is maximum. And as the error keeps on increasing to the negative or towards the positive as well, the frequency keeps on decreasing. So let's say we're talking about a line with a distance 30 meters. So if you keep on taking that reading again and again with instruments, and just to visualize it, let's say it's not 30 that we're talking about 30.765, right? And the probability that the next time when you keep on taking that reading, it will be close to 30.765, that's more probable. So that's why when the residual is smaller, the frequency of readings will be more in that particular range. And there's a very little chance that you would come up with a reading such as 43, far away from the most probable value. So the chance of that is very small. And that is why as the residual value increases, the probability or the frequency of that value keeps on decreasing. So once you plot these values and then you join them using this smooth graph, you get a graph that looks like this, and this is called as frequency distribution, or this is called as a normal distribution curve. So interesting that we call this as a normal distribution curve because um, in probability, you can have different distributions. You can have triangular distributions. Um, you can have uh, polynomial distributions. So you have a whole bunch of different distributions that you can get in probability, in theory of probability. But with random errors and the topics that we're discussing, we get a distribution which is called as a normal distribution. And what's interesting about this normal distribution is that by calculating area under the graph, um, you can then assign probabilities to different values of the residual. So what I mean by that is that this is a probability distribution basically. And the area under the curve is equal to 1. because the sum of probabilities is equal to 1. And then you can assign probabilities to different values of residuals. So if I say that what is the probability that the next time the error would be in this range, we can calculate that. And if I say that what is the probability that the error will be in this range, the probability would be more than this probability over here. So this is how, by assigning residuals to their frequencies and by plotting this graph, we can actually calculate probabilities of errors and then use those probabilities in our calculations. So some facts about the normal distribution curve. So the curve's bell shape is characteristic of a normally distributed group of errors, and thus it is often referred to as normal distribution curve. The area between ordinates constructed at any two abscissas of a normal distribution curve represent the percent probability that an error of that size exists, something that we just discussed. Since the area sum of all bars of histogram represent all errors, it therefore represents all probabilities, and thus its sum equals 1. So likewise, the total area beneath a normal distribution curve is also equal to 1. So since we are taking, so that's probability, right? The sum of all the possible events, the probability of all the possible events occurring, that is equal to 1. So since on that graph, we take all the residuals that we encountered, so that means that is the probability that we're working with. And then you plot it against um, their expected or their occurrence or the frequency of their occurrence. That means in this graph, we have covered every possibility. So that is why the sum is equal to 1. If the same observations of preceding example had been taken using better equipment and more caution, smaller errors would be expected and the normal distribution curve would be taller and narrower. So let's see these two curves, one on the left and one on the right. So the difference between the two curves is that, well, the similarity is that both are normally distributed curves. But the difference is that the curve on the left is narrower and taller, and the curve on the right is smaller and it's wider. And that is because in the left one, the residual values are smaller, and on the right one, the residual values are bigger. That means the precision is more in the left curve and the precision is lesser in the right curve. And there can be a number of reasons for that. One is, let's say in the left set of observations, we took the observations with a more precise or better equipment. Another explanation could be that all the observations were taken by the same person. And in the curve on the right, all the observations were taken by different set of people or by an instrument which was less precise or which was older, in which the errors could be more or something like that. But you can see how the normally distributed curve can change depending on what the data represents. So just by looking at raw data, you won't be able to comment on the precision, the level of precision or level of accuracy. But once you have this normally distributed curve, you can quickly comment about the health of the data or the health of the observations. So these are the laws of probability that small residuals, errors, or observations which have little difference from the most probable value, the probability of their occurrence is more, and the probability of occurrence of large errors is smaller. So large errors happen infrequently and are therefore less probable. And for normally distributed errors, unusually large ones may be mistake rather than random errors. So if you encounter an observation which is very far apart from the most probable value, that means there isn't just random error, there are systematic errors or mistakes in that value. And that shouldn't be used in the calculations of probabilities because we are calculating probabilities for random errors, not for systematic errors. Positive and negative errors of the same size happen with equal frequency, and the mean of the errors is equal to zero. So this is something that we discussed before as well, and you can judge by looking at the graphs also. So the graphs are mirror images towards the left side of the vertical axis and towards the right side as well. That means there is an equal chance of an error of equal magnitude um, occurring, and also the number of times that it occurs is also same. So that is why the sum of positive and negative errors equals to zero, or the probability of occurrence of a negative error and the probability of occurrence of a positive error of the same magnitude is the same. That is why the sum of residuals is equal to zero. So although the curves have similar shapes, the two curves that we saw, the narrower and the taller one and smaller and the wider one, there are significant differences in their dispersions. That is, their abscissa widths differ, and the magnitude of dispersion is an indication of the relative precisions of the observations. So if the curve is narrower and taller, that means the precision is more. And if the dispersion is more, that means the precision is lesser. One other way you can comment on their accuracy is by using the term standard deviation. And standard deviation equation is given by plus minus under root summation of residual squared divided by n minus 1. So let's say you have five observations, and for those five observations, you calculate the most probable value, which is the average of those values. Once you have that average, you can subtract each value from that average one by one, and that would give you five residuals. Then you square those residuals, take their sum, and divide it by the number of observations, which was 5 minus 1. Take the under root with a plus minus sign, and that value would be your standard deviation. Now, see how in the numerator they have taken residual squared and then taken the summation. That is because we've already discussed that the sum of residuals in a large set of observations is equal to zero. So if you don't take the square, then the sum would just be equal to zero. That is why they've taken the square as well. And this whole equation gives you standard deviation. And in the next lecture, we'll start from here and we'll discuss what actually standard deviation represents and how do you interpret the value of standard deviation. So until then, Allah Hafiz.